Hello, I'm Daniel Iseli. I'm a senior customer technical support analyst and part of the Uniface customer and sales support team. Today I'm here to provide you some information about structs in Uniface. To start, I would like to go through the agenda of this presentation. Firstly, we will look what a struct is. Next, we will discuss how we can use it. And finally, we will discuss some best practices. The last part is based on the experiences that our Uniface 10 development team has shared with me. Okay, let's start. The purpose of structs. What is a struct? It is a tree-like data structure in memory that is used to dynamically manipulate complex data. It can be used to transform complex data from or to XML or Uniface component data. And in one of the coming releases, we'll plan to introduce JSON transformation. From talking with our product manager Adrian Gospel, I've learned that most of the development work is already done. We just need to finalize it. Here we can see a graphical representation of how a struct looks like. So, it is a collection of data objects or nodes that are hierarchically organized under a single root node. A node that has a parent node is a struct member. A member can be a struct itself, in which case it is called a nested struct. A struct exists only in memory, and it exists only as long as there is a struct, variable or parameter that refers to it or one of its members. Now I would like to show you in a short demo how a struct looks like in Uniface 9.6. So we start Uniface. Here we have a simple form, and on the left side there you can see some data. It's from an order record. And when I click on the button, it will create a struct. When we look at the struct, we already can see, as we discussed before, it looks like a tree-like data structure. We can see also the different nodes. The root node on top here has the name acme001. And if we check the type beneath it, then we can see that it's a component. Underneath the component, we have a node called orders.acmeord. And from the type, we can see it's the entity. So this is the main entity here on the left. As any entity, we have an occurrence here. And in the occurrence, we have the fields with the data. Here we can see the ordnum field with the value 60, the order number, the order date, 6th of June 2009, and the shipping date, which is 16th June of 2009. Underneath here, we can see that the struct also contains a node with an inner entity called customer. Again, the customer entity has an occurrence with some data in it. We can see here the ID of the customer. The first name, Ramona, and the last name, Wright. Okay, that should be enough for the start. I will explain the details of what we've seen here in the coming slides. Let's go back. Structs and members. A struct is a data structure consisting of one top node and 0 or more subnodes called members. Each member can hold a scalar data value, such as a number, string, or date, or it can hold another struct, in which case it's a nested struct. A struct or struct member can have a name. If it has a name, the name is case sensitive. And if it's a nested struct, it is known to its parent by its name. The name can consist of an empty string. And different members of a struct can have the same name. Struct members are sequentially ordered They can be addressed by their index position, making it possible to address a specific member even if it has the same name as another member or no name. Next we'll cover struct leafs. A leaf is a struct member that has no value or only a single scalar value. However, adding another member to a struct leaf implicitly changes it to a nested struct. The value of the formal leaf is now held in a nameless struct known as a scalar struct, and the nested struct has a mixed data structure. A book is, for example, a complex data structure that can be represented by a struct. This illustrates a number of characteristics of a struct. For example, the book struct contains members called title, preface, and chapter. A struct member can have a value. This can be, as we discussed before, a scalar value. And here, for example, the value of the first title member is a string getting started. A struct member can, of course, also have as value a struct. For example, each chapter is a nested struct because it has child members. And a struct can hold a mixture of both scalar members and nested struct members. For example, the book struct contains two scalar members, title and preface, and two nested structs, chapter. Members of a struct can have the same name. For example, there are multiple members called chapter and section. Thus, if a struct variable references a struct by name, it contains a collection of references to all structs with that name. And we also discussed that struct members are sequentially ordered. They can be addressed by the index position, making it possible to address a specific member even if it has the same name as another member or no name. An example for this is the chapter. First member we can address with the index 1 and the second with index 2. Struct variables. A struct variable does not contain the value. Instead, it contains 0 or more references to struct nodes. One struct variable can contain multiple references to different struct nodes, and several variables can refer to one struct node. Here we have an example for this. Several struct variables can refer as said to the same struct. For example, the variable vBook and vStruct both refer to the struct book. And a single struct variable can refer to multiple structs, which makes it possible to manipulate a group of structs instead of handling them individually. For example, the struct variable vChapters contains a collection of structs named chapter. Struct parameters. Structs can be passed as parameters by reference or by value. The content of a struct parameter is not a struct, but 0 or more references to struct nodes, just as it is for struct variables. This is in contrast to scalar data types, such as strings. The default behavior is to pass struct parameters by reference in partner operations and entries, and by value in public operations. When passed by reference, the parameter passes a copy of the reference to the called entry or operation, so an additional reference to the same struct is created. When passed by value, a copy of the struct is made. It is possible to override the default behavior by explicitly defining how struct parameters are passed using the by_ref or by_val qualifiers. This can be useful if you know that the calling and receiving component instances are running in the same process. If neither the by_ref nor the by_val qualifiers are used, the default behavior depends on whether the parameter is declared in a public operation or not. However, because of the functional differences between the two, it is advisable to explicitly specify the intended qualifier. References are memory pointers, so it is only possible to pass them between proc modules that share the same memory. This is always the case for partner operations and entries, but may not be the case for public operations. If an operation with a by_ref struct parameter is activated in a component running in a different process, this will result in a proc error. This proc error is -73. Operation with by_ref struct parameter cannot be activated across processes. Next, we'll cover the struct access operators. There we have the dereference operator by name. It returns a collection of references to all struct members with a specified name. It looks like this. So here we have v book struct dereference chapter. And to make it more visible, here we can see how to access the member by name. For example, with this instruction, we get all struct members named chapter. Next, dereference operator with an asterisk. When used with the asterisk wildcard, it returns a collection of references to all members of a struct. This is a special case. And it is important to note the asterisk wildcard can only be used after the dereference operator, like this. It cannot be used in constructs such as vstruct dereference c asterisk to get all structs whose names begin with C. This is not allowed. Here we get an example of the v book struct dereference asterisk wildcard. And if we do this, we get all the members of the struct referred to by the variable vbook struct. This returns the title, preface, and all chapter members. Next, the struct index operator. It returns a reference to a single member of a struct based on its index position in the collection of references. And you write it like this: vbook struct dereference chapter index 2. And here's an example. With these instructions, we access members by name and index. For example, get the second member named chapter. We can also access a struct from a collection by its index position regardless of its name. This is using the asterisk wildcard. For example, if I specify vbook struct dereference asterisk wildcard index 2, I will get the second member of this struct. Next, we'll cover the proc instructions for manipulating structs. Here's the list. First, we have the struct data type for variables and parameters. Then we have the $new struct function that allows you to create a new empty struct. Then we have the component to struct and struct to component instructions. This will allow you to convert either from Uniface component data into a struct or load data from a struct into a Uniface component. And we have the same instructions for XML. These are XML to struct and struct to XML, which allows you to convert XML data into a struct or convert a struct data into XML. And then we also have a function called $equals struct refs. With this, you can check whether struct variables point to the same struct. Then we also have a number of struct functions. First, we have the $dbg string and dbg string plain. The first one will get a string that represents the struct or struct collection, and the second one will basically do the same but without annotations. Then we have the $call size function, which will get the number of structs in the collection. $member count will get the number of members in the struct. And then we have three functions to check whether a struct is a struct leaf. The logical endpoint in a struct tree. We'll do this by $isLeaf. Then we have a $isScalar that allows you to check whether a struct is a scalar struct. And last but not least, we have $isTags, which we can check whether a struct is a $tag struct for another struct. But there are more functions. Then we have $index, which allows you to get or set the index of the struct in a struct collection. $name, which allows you to get or set the name of a struct. With $parent, you can get or set the parent of a struct. With $scalar, you can get or set the scalar members of a struct. And with $tags, you can get or set the annotations of a struct. Although most struct functions only return information, there are 3 functions that can be used to change data. You can use $index to insert a member into a struct at the specified index, $parent to move a struct member from one struct to another, and with $tags you can set the value of annotations or define your own annotations for use in conversion routines. Now we discuss what struct annotations are. Struct annotations are descriptive data elements that are also known as tags. They contain information that is used to correctly convert data to and from specific formats or to interpret data correctly. Each struct node has a special child struct to hold annotations. This struct can be accessed using the $tag_struct function and is therefore known as a $tag struct. Unlike normal struct members, annotations have no specific position inside the struct, and are therefore not counted or treated as members of the struct. This is in contrast to, for example, XML processing instructions, which are treated as normal struct members because their position in an XML document is relevant, even if they are not part of the document contents. Struct annotations for data conversion. Struct annotations are specific to a complex data format. Structs converted from Uniface component structures have only one annotation tag set, UType, which indicates the type of Uniface object a struct or struct member represents. There are more annotation tags available for XML-based structs. The proc conversion routines, component_to_struct and XML_to_struct set annotations, whereas struct to component and struct to XML use the annotations to guide the conversion process. For example, when transforming from XML to Uniface, a tag called XML class contains information about how the data was stored in the source XML, for example, if it's an attribute or element. This is useful when doing a round-trip conversion, so no information is lost. Some data formats have their own metadata, which can be added as annotations. For example, the XML doctype specification and XML declaration are required in XML data. Because annotations always apply to a specific format, they're ignored when converting to other formats and will be lost. For example, XML annotations are ignored when converting from a struct to a component. When converting between XML and structs using XML_to_struct or struct to XML, you can set and retrieve annotations that provide information that guide the conversion or reverse the conversion. As said before, you can use the $tags function to set or get the value of an annotation for a specific struct. Here we can see the root element has the tags XML version and XML class. This is a document. The first element is called Uniface, as we can see by its tags, and the element has 2 attributes called release and XML engine. And the third one is an element called table. You also can see a comment here in the XML. This is not converted to a struct by default. You can add it if you want to, but it's not there if you do the plain XML_to_struct instruction. Here is a list of annotation tags for XML struct conversions. I won't go through them all. This is just as a reference for you to have a look what is available. And there is even more. Next we'll cover how to create a struct. This can be explicitly by using the $newStruct proc function. And it looks like this. vstruct equals $newStruct, which will give you a struct. A struct can also be created implicitly. This can be done by assigning a value to a struct variable parameter. For example, like this. Here we assign the string myBook to the struct variable vstruct. Or we can implicitly create a struct in the following ways: assigning a value to an allowed struct function, $name, $parent, or $scalar, or to $tags. For example, with this instruction vstruct dereference $name equals mybook, we will create a new struct with the name mybook. Note: struct access operators, such as the dereference operator and the index operator, enable you to address structs and their members by name and index number. Struct functions enable you to get and set the values and properties of structs and their members, and insert, copy, move, and remove them. But there's more. We also can create a struct implicitly by using one of the conversion instructions, such as XML to struct or component to struct. With this instruction, XML to struct vstruct, book.xml, we will load the content of a file called book.xml, and the contained XML will convert it to a struct. Next, we'll cover how to delete a struct. A struct, as we said before, exists only in memory, and as long as there is a struct variable or parameter that points to it. There is no proc command to delete a struct. Instead, a struct is deleted as soon as it is no longer referenced by any struct variable or parameter, or is no longer owned by another struct. For example, reassigning the vstruct variable to another value deletes a struct it refers to. In this case, we assign an empty string. Here we have the same again. What will happen when we assign an empty struct to the variable vstruct1? This will be deleted. You can see node 1 to node 3, they're not there anymore. However, node 4 to node 6 are still present since they're referenced by the struct variable vstruct2. Next, we'll have a look at how to use the structs. With its struct data type, Uniface enables you to perform dynamic transformations of complex data structure. For example, convert XML data received from web services into data structures that easily can be accessed within Uniface, such as a component data structure. Convert the data in a Uniface component into a nested XML data structure. Merge data from different components for use in another component. And extract desired information from any type of complex data structure. You can use the proc instruction XML to struct and struct to XML to convert complex data from and to XML. XML can be much more complex than Uniface components data because it supports unlimited levels of nesting. It also has data types that are not recognized by Uniface, and doc type declarations and schemas which define the structure but are not actually required in the struct itself. For example, XML comments, doc type declaration, namespace declarations are usually ignored when converting to structs, although they can be included if required. If you're converting from a struct to XML and you need these XML constructs in the output, you need to explicitly define them. Here you can see a basic struct that represents XML data, and it has the following structure. 1. A top-level struct for the document can optionally have attributes for the XML declaration. 2. Named struct node with element name. 3. Named struct with attribute name. Attribute structs must precede any child elements. 4. Named struct leaf with element name. 5. Named struct with application name. In the next demo, I would like to show you how we can transform an XML stream. For this, we'll use a CD catalog. You can see here on the screen one of the records from this CD catalog. And what we were going to do is we would like to convert this XML into the XML we can see on the lower right. How are we going to do this? First, we will take the element title and convert it to an attribute. Next, we will add a prices element. And after this, we will move the current price element to the newly created prices element and make it a child element. Next, we'll add a currency attribute to the price element, and we will assign the value US dollar to it. In the next steps, we'll create a price in euro. For this, we copy the existing price element, and we will change the currency value to euro, and we also will recalculate the price. And the last step, we'll do the same again, and now we'll create a price in British pounds. Okay, let's start Uniface, and let's see how we can do this. On the left here, as said, is the source XML stream with the CD catalog. If I press on the button, XML to struct, you can see on the right the resulting struct. In order to make it more readable, I will hide the annotations. And now you can see just the structure of the struct and the data. In the next step, we're going to convert the XML as I've just explained to you. And this is the proc code we're going to use. In the first step, we will get a reference to the CD collection. You can see this here. So this is the struct variable, the catalog member, and here we get the CD members. And we assign this reference to a variable called vStructCD. In the next step, we're going to calculate how large the collection is, the collection of CD members. We do this by querying $call size for the variable vStructCD, and we are going to assign the return value to a numeric variable called vCallSize. In the next step, we're going to loop through all the members of the CD collection. And in this loop, as first step, as mentioned, we're going to change the XML class of the title to attribute. You can see this here. We do this by changing the $tags XML class and assign the value attribute. In the next step, we're going to create a new struct member called prices. We do this on the current node. And we do this by using the proc function $new struct. In the next step, we're going to change the parent of the price struct member by using the $parent function. And the parent will be, after this, the newly created prices struct member. So we're going to move the price struct member to the prices struct member. In the next step, we're getting a reference of the prices member, and we assign it to vStruct, to the variable vStruct prices. In the next step, we're going to create a new struct member called currency. And again, we use the $new struct function for this. In the next step, we're making sure that the currency struct member is the first one, is the first struct member here. And we do this by assigning the value 1 to the $index function. In the next step, we're assigning the string US dollars to the currency struct member. Then we're going to say, or we're going to define that this is an XML attribute. We do this by defining the XML class tags. In the next step, we're getting a reference to the price struct member we just changed. We assign it to a variable called vstruct price. And then the next step, we're going to add a new price struct to the collection. And we do this by assigning the vstruct price variable to that new struct. What we do here is we will copy the price struct and assign it to this newly created struct member. Then we're getting another reference to that newly created price struct member. We're going to change the value of the currency struct member to euro. And the next step, we're going to recalculate the price in euros. And we do this by assigning the recalculated price to the scalar value of vstruct price 2. After this, we do the same as above. We create a new price struct member. Again, we are copying the original price struct and assign it to this newly created member. Now we're changing the currency to British pound and recalculate the price. So these are the steps we're going to follow, and I said this loop will be done on all the members with the name CD. Okay. Let's do this step by step in the code. Step 1, as we said, we assign the reference of the struct catalog CD to the variable vstruct CD. You can see here, this is the resulting, or what the variable vstruct CD refers to. Here again, you can see the corresponding proc instruction. In the second step, we change the element title into an attribute. We don't see this here since we've switched off the annotations. When I bring back the annotations, you can see here that the title is indeed now an attribute. Okay, I'm going to switch off again the annotations to make it more readable. In step 3, we create a struct member called prices. You can see it down here, it's empty. In step 4, we move the price struct member to prices. You can see here, the price struct member is now a child node of prices. In step 5, we create an attribute called currency for the price struct member with a value US dollar. You can see here the value US dollar. And if I switch on the annotations again, you can see indeed it's an attribute. In step 6, we create a second price member with the value euros by copying the first one. You can see here is the first price struct member, and here's the newly created second one with the price in euro. And in the last step, we create a third price member with the value British pound, and you can see it here. Okay. Now you can see here on the right, we have the changed struct. And if I now press on this button, struct to XML, I will convert this data back to XML. You can see here on the left is the original one. And now that I've clicked on it, you can see the changed XML. Again, we can see here the title attribute. Here we have the prices element. And here we have the three prices in US dollar, euros, and British pounds. Okay, that concludes this demo. Let's go back to the presentation. You can use the proc instructions, component to struct and struct to component, to convert complex data from and to a Uniface component. A struct that represents the data in a Uniface component has the following structure. You can see it here. First, named top-level struct with the name of the component. Second, named struct nodes for each entity in the component structure. Third, named struct node with a fixed name OCC for each occurrence in an entity. Fourth, a named struct leaf with the name of the field. And fifth, named struct nodes for each entity that is a child of an occurrence. Entity and field names may be partially qualified. For example, field name.endName, or fully qualified entity.model for an entity, or field.entity.model for a field. Field names can normally be unqualified as they are implicitly qualified by the location within the context of an entity. In case of conflict, identical names of a field and an entity drawn on the same level, names must be fully qualified, or tags can be used to specify the type of the object. For each struct member, the UType annotation defines the type of Uniface object that the struct represents, if it's a component, entity, occurrence, or a field. When converting to structs, component to struct automatically provides the UType annotation. When converting from structs, using struct to component, the outcome may be undefined if the struct name matches more than one field or entity. Next, we'll transform the component data with the structure we can see on the left here. Three nested entities called customer, address, and country. And we'll convert it to a single entity with the structure we can see on the right. How are we going to do this? First, we copy the data to a struct. In the second step, we move the field nodes of country and address to the level of the customer node. Next, we'll rename the former node nmCountry to country. That's the name of the country. Then we rename the node customer to new customer. And in the last step, we'll copy the data to the destination entity. Okay, let's do this again in Uniface. Start it. And you can see here the entity highlighted in this dark blue color. This is the data we would like to transform. So in the first step, I do component to struct. And on the right, you can now see the struct of the data. You can see here the customer entity with its fields. And we have an address. If I scroll down, we have here the country. Okay. Again, I switch off the annotation to make it more readable. Now we just have the struct, the structure of the struct, and the data. Now we go over here, where we can see the target entity. Now I would like to show you the proc we're going to use to do the transformation. First, we're going to assign the customer OCC member to a variable called vStructCustomer. Then we're going to assign the address OCC member or collection to the vStruct address variable. And we do the same for the country OCC collection, which will be assigned to the vStruct country variable. In the next step, we're going to change the parent of the vStruct country and vStruct address of the members in there. We're going to assign it to the vStruct customer. So basically what we're going to do is we're moving the struct address and the struct country to the same level as the customer struct. In the next step, we're going to delete the country and the address structs since we don't need them anymore. In the next step, we're going to rename the NM struct member to country. We do this by assigning the string to the $name function. We're doing the same for the customer struct member. We're going to rename it to new customer. And in the last step, we're going to copy the data to the target entity by using the struct to component instruction. Okay, let's do this step by step. As said, first we do the assignment of the three here, the vstruct customer, vstruct address, and vcountry. Here you can see how the vstruct customer variable looks like. In the second step, we move the members vstruct country to vcustomer. You can see them down here. These were the child nodes of country. And if you go up here, you can see country OC is now empty. In the next step, we move the members from vstruct address to vstruct customer. Again, on the bottom here, you can see the former members of address and then all part of customer. Again, here is the empty struct country. Now we're going to delete them. You see that the country and the address struct are gone. We rename NM to country. You can see it here. Now we rename customer to new customer. You can see here the changed struct member. And in the last step, we copy everything to the target entity. So that's it. Let's go back again to the presentation. The ability to transform complex data from one format to another is a common requirement. For example, web services often use and produce XML that does not directly correspond to Uniface data structures, such as entities and lists. For Uniface applications to consume or produce complex data, it needs to be converted to or from Uniface entities, lists, or XML streams. In the next demo, we will call a web service called Music City. We will convert the XML data that is returned by the web service to a struct. Then we'll transform the struct to match the component structure. And as a last step, we're going to load it. We're going to load the struct into the component. And here you can see how the XML looks like that is returned by the web service. And here on the right, you can see the component structure to which we would like to copy the data. We're going to achieve this by transforming the XML to a struct, change the struct, and then transform the struct to the component. Okay, let's show that again in Uniface. Here we can see the form. I'll enter an artist ID. I call the web service. In a couple of seconds, we should see some data. Okay. So here you can see the data returned by the web service. On the right, we can see the struct. Again, in order to make it more readable, I will disable the annotations. Now we can see just the structure again with the data. And you can see here that this information is for an artist called Anton Karas. Okay, let's go to the target entity. You can see it on the right. This is where we would like to copy the data to. And here is the proc code we'll use. And here is the proc code we use to achieve this. In this demo, we're going to use a recursive loop. But first of all, we are going to move the artist struct member a couple of levels higher to the root node, since we don't really need the parameter and the artist struct members. So this is what we do here. In the second step, we're going to delete the struct parameter, or we're going to delete the struct parameter. And after this, we're going to call the routine process struct. And what it does, we're going to loop over the struct collections recursively, adding a new node for the occurrence member. The entry body adds the member to the struct that was passed in, but not to its children. To deal with the child level, the entry calls itself recursively. When a collection is passed in, the entry calls itself for each struct in the collection. The action is applied to individual structs only, or more precise, on collections with the collection size 1. Okay, how does this look like? We go down here. Here we check the collection size. If it's larger than 1, we're going to loop through the collection. And here we have a check. If the struct we're looking at is scalar, then we know that it has to be a field in this case. So we're going for any struct that is not scalar. And then we are calling in, just passing that one struct member. And once we're down here and the collection size of the struct we pass in is 1, again we do, for safety reasons, do the check. If it's not scalar, yes. So here we have a variable, and we add a new struct member awk to it. Do this with new struct. Then we're going to move all the struct members from the import parameter pstruct to the newly created vstruct. There will be child nodes of the occurrence member. And then we're going to move everything back. And what we've done here effectively is we've added a level into the struct. And this level is the occurrence struct member. Okay, we're calling this recursively as said, processing everything. And now we're going to do this. In the first step, we're going to move the parameter artist struct member to the same level as a root. You can see it here, parameter artist. And we're going to move the artist to the level of the root node. Here's the struct before. I click on it, and you can see it has moved. If I move it down, you can see also that the parameter struct is gone. In the next step, we're moving artist to artist awk. So you can see here artist with all its members underneath it. And we're going to add a new occurrence struct and move all these members to that newly created struct. Okay. And here you can see the newly created awk struct member, and everything has moved one level down. And now we do this for all the other stuff. Here we can move country to country awk. There it's added. Now we do this for artist credit name. There you can see the new Struct member. Same for artist credit. Now it's been added. Release group. And we'll do this a couple of times until we're finished. Okay. Now you can see here on the right, the data has been copied to the entity. However, you also see we have two fields here, last updated and created. And if we check the struct, you can see here is the last updated. It's a string value that represents an XML date value. And this format cannot be understood by Uniface, obviously. And we could create a routine that would do the conversion for us. On the next demo, I will show you an alternative. Okay, let's go back to the presentation again. The XML to struct instruction also has a /schema switch. If /schema is not specified, the Uniface data type of every element and attribute is string. If the /schema switch is specified, elements and attributes with predefined data types are included in the struct as scalar structs of matching Uniface data types. The values themselves are converted to Uniface format. But before we do the demo, what is an XML schema? An XML schema is a XML-based alternative to DTD. It describes the structure of an XML document, and a schema language is also referred to as XML schema definition, or XSD. So the purpose of an XML schema is to define the legal building blocks of an XML document, just like a DTD. An XML schema defines elements that can appear in a document, defines attributes that can appear in a document, it defines which elements are child elements, it defines the order of child elements, it also defines the number of child elements, it defines whether an element is empty or can include text, it also defines data types for elements and attributes, and last, it defines default and fixed values for elements and attributes. Here are two XSD files we'll use for the next demo. This first, the parameter XSD that describes the Uniface return parameter of the web service operation we're calling. You can see here it has the namespace URN :Uniface :applic :complex parameter. You see the relevance on the next slide. And here's the second, the music cityplex XSD that describes the data returned by the web service operation we're calling. And this has the namespace URN :Uniface :applic music cityplex. And how do we use all this? Here you can see, first we create a schema list, and we do this by namespace. You can see here the namespace of the first is XSD and its location. It's in the file parameter.xsd. And we do the same for the second namespace and its location in the music cityplex XSD. The schema list is then passed to the XML to struct /schema instruction, and it will do the conversion. Okay, let's have a look how this is working in the practice. Okay, we have basically or nearly the same form as in the last demo. We're again going to retrieve the information of the artist with the ID 332. Wait a couple of seconds. Okay, here's the data returned. One on the right side, you can see the struct again. And if you look closely, you'll see that we have a couple of new tags. Here we can see This is a data type parameter, and it's a complex type. And also here you can see the corresponding namespace. Here you can see all the different types and namespaces. And this is a result of using the schemas. I'm going to switch off the annotations again to make it more readable. And if you look down now to the value of last updated, we can see that it is in the internal format of a date and time. Okay. Going over to the right here. The routine to do the conversion is quite similar to what we used in the last demo. I'm not going to show you everything in detail anymore. I just will do the conversion. Again here, you can see the last updated value and the created value. And if I click on the button, indeed, you can see here the last updated value. The 2nd September 2011, 6:23. And the created is 14th February 2012, 14:10. Okay. Now I showed you how we could convert different data types from XML data to Uniface using an XSD. And if you need to know more info about structs, then you go to the Uniface library. It includes a lot of information which are quite useful. It also includes a set of examples. You can copy the code to a component, run it and debug it, and you can see what it does. Okay, we're now getting to the last part of this presentation, the best practices. Structs are key to the architecture of how we're building the Uniface 10 IDE. Here you can see a screenshot of how the version 10 IDE looks like. It's still work in progress. And how are structs used in the IDE of version 10? The data is loaded from the repository into a controller component, and from there the data is passed to the views the developers see. The data is exchanged in a structured way, and it is of course managed using structs. And what are the direct spin-offs of using struct in the development of version 10? One of them is more efficient use of memory, performance improvements, consistency improvements, and also documentation improvements. And the good news is a lot of these improvements are already available in Uniface 9.602, so you can use this already today. Now here are some best practices the Uniface 10 development team has gathered while building the version 10 IDE. These are not specifically related to structs. The lessons learned boil down to basic programming principles with respect to dynamic loops. And this is not only applicable to structs, but also to, for example, a collection of entity occurrences or a list with members. So what would you have here? You should avoid looping through a struct too often, so minimize that. You should also minimize the amount of proc code in the deepest branches. What does this mean? You can see here an example. In each instruction, Uniface has to go from the highest level, from the root node, down to node 11, 21. On the lowest level, we're assigning a value to it. And for each instruction, Uniface has to go through the whole struct, starting at the top, going down level by level by level. This is not very efficient. So what is a better way to do this? You first assign one of the lower levels or struct nodes to a variable, and in the following instructions you used the variable with the reference. This is much more efficient. Uniface doesn't have to go through the whole struct again and again. It will start at node 2.1, and this is, of course, much better. What else? You should use by reference wherever possible instead of by value. It is, of course, easier to just assign a memory pointer instead of changing the complete struct or passing the complete struct value. Should also minimize the usage of $call size and $member count. Why is this? We have here an example for a loop. And if you look at this, for each iteration of this loop, Uniface has to recalculate the value of $call size. That is, again, not very efficient. So what is a better way to do it? It's kind of obvious. You assign the value of $call size to a numeric variable, and you use the numeric variable instead of $call size in the loop. And it's also more efficient to address struct members with the asterisk wildcard instead of the name. So wherever possible, you should not use the name. Okay, this is the end of my presentation. I just want to summarize what we've just done. So, structs are used for manipulating complex data. Structs can be used for transforming data sent to and received from web services. And structs will play an increasingly important role in Uniface, for example, in version 10. Okay. Thank you very much for watching, and bye-bye.